You missed all that. Hi, everyone. This is Mr. Vallejo in the VRC Chemistry Laboratories. I was just going over before I started recording what we're doing today. And our three main things is I'd like us to read. Now I'm back to normal. I'd like us to read 15.2. We did 15.1, but let's do 15. Oh gosh, it's not that short. Oh well. Let's do it though. All right, I'd like you to read 15.2, and then we'll go over the answers to page 501. Let's discuss 501 together, 10 to 17. Do that first, and then while you're reading, I'm going to go and see if I can get the rest of the lab equipment for the lab on page 508. We'll try to do that second. And the third thing I want to do is I want to do my favorite foldable with you. You like foldables? I love foldables. Yeah, I mean, sometimes it's kind of middle schoolers. I go, oh God, but this one is like adorable, you know? So we're gonna do that. And there's something on your list, on your Anastasia, what'd you call it? Your list of assignments that you do, that you have to do in order to get with the learning program, LP. Yeah, all right, you got it. I got it before I saw your note though. So on your LP, you have a list of 13 items to compare. Like, what's the difference between this and this? So we're gonna make a shmush book. I love saying that word. Shmush. You know, like when you have a cockroach, a cucaracha, and you shmush him. These are called shmush. These are called shmush books. And so for that one, you're going to need scissors and 2 sheets of printer paper. Okay, scissors and okay, all right. That's my alarm. And so yeah, 2 sheets of printer paper and some scissors, and then we can do that foldable together. At least set it up, and then I mean, the rest you can do on your own, I suppose. But I'm going to show you how to do this in case, and this is like a life skill, because once you know how to make this foldable, you're going to go, oh, but then you're going to use it for life, you know, like couple of Valentine's days ago, I made my wife a shmush book, and like now she keeps it in the back of her wallet. It's one of those things you just keep, you know. So I'll show you how to make one. In biology, we do it like almost too much. And so they have a collection of shmush books. Or what is a shmush book? A shmush book is from one piece of paper, you make a little teeny tiny book that's this big, and it has 8 pages in it. Oh, how cool is that? So if you can think of anything that has 8, like we first did it for, have we done one in chem? I don't think we have. So I'm going to show you how to do it, and then once we do it, but there's 13 items, so you're going to need more pages. You're going to have 16 pages by the time you're done. So we're going to put it together. So I think that's pretty cool. If you think it's childish, well, forget you, because I think it's a pretty cool thing to do. So we're going to do that. Jaden's in the room. I got to take a quick break because the recording is on. And let me turn it. I am going to resume the recording, and we are doing number 14. And what we have to do with number 14 is it says, what is the percent of mass of water? All right, so the percent by mass of water would be the mass of the water divided by the mass of the whole thing. So you got to figure out what all those are. So if you look at it, this has 7 water molecules because it's a heptahydrate. And because it's 7, what we got to do is, where's Mr. Calculator? No. There it is. My power went out this morning and all my clocks are like a microwave. It's goofed up. The only things that are going on are the phones. So gotta go reset that stuff. Oh gosh, and now the landscape lighting is gonna be off again. It's hard to reset for me. All right, so 7 water molecules. Now let's just do 1 water molecule, but you can do this in your head. Well, I'm not gonna say that here. Okay, here's the oxygen. Oxygen has if you look at the periodic table of elements, oxygen is 8 and 15.99999, which is really 16. Okay, so oxygen is 16. Hydrogen is, if you look at the periodic table of elements, it's hydrogen and it's 1, that's 1.008. So, which is essentially 1, right? So each water molecule is going to be 18 grams per mole. Okay, so in order to get the weight of water, the mass of water, we want to speak properly, because remember, weight is dependent on the attraction between two objects, the gravitational attraction. Okay, so it's going to be 18 times 7, which is 126. So 7 water molecules are going to weigh 126, 126 grams of water is what 7 moles of water is. But that's not it. That's not everything. You've got this stuff too. You've got iron, you've got sulfate or sulfur, and you got oxygen. Now iron, I think it's 55. See, I don't know. So I'm going to look it up. You probably already looked it up. I don't know. Is it 55? Anyone know? I got to go to the back of the book. Iron is, where is it? 26, 55.847. 55.8, that's, well, let's say, you have 1 iron. So in order to figure out the mass of this right here, you got iron, which is 1 times, what did I say, 50, oh boy, 55.8, 55.847 grams per mole from the periodic table. So 1 times 55.8 is 55.8. And then we have a sulfur. Sulfur's 32, right? So 32.06. So it's 1 times 32.06, which is 32. 32 times, oops, 1, 2, 1. 32 times 1 is 32. And then times 4 for oxygen. You have 4 oxygens. 4 times 16. We saw from over here, 16.0. We want 16 is 32. 32 twice is 64. So you get 64.0. So to get the total weight of FeSO4, that's going to be 8. That's going to be 9 plus 2 is 11, carry to 1. 8 plus 1 is 9. 9 plus 6 is 15. 151.8 grams. Okay, but here's the tricky part, and this is where people goof up. It's not 126 over 156, because what we were trying to figure out is the percentage of mass of water, mass sub water, divided by the mass of the whole meal, the whole. And the mass of the whole is not just 51, because the mass of, although this is, we know this here. All right, the mass of water is 126 grams per mole, or per mole of this thing. So we have 126 grams in this whole hydrate. That's the water. But then the mass of the whole thing is going to be 151.8. That's this part. And then you've got to add this part, this second part, which is 126. It's an add though, it's not a multiply. And so you can't cross them out. Some people are going to cross them out. That's not right. So, hey Siri, 158 plus 126.
That would be 284.
So I got 284 and I got 126. So then let's go over here and say, hey Siri, 126 divided by 284.
That would be about 0.4436.
0.4436. And so that's going to give us looks like 3 sig fig is going to be 0.444. And that is going to be, what was the question? The question was, what's the percent, right? So you've got to express it as a percentage. Gosh darn, I could have sworn I put a posted in there. I did, it's just not sticking out. Okay, so there it is. And the question is, what is the percent by mass of water? So this is by mass of water. And if it's a percent, that's going to be 44.4%. So it's a percentage. And then you box your answer. And then you showed your work right there. Woo, 44.4%. Right, let's see. Looks pretty good. I think we're doing all right on that. Unless I made some kind of math there again, because I'm looking at the answer, and the answer says 45. So 45, I got 44. Is that significant? Let's see. Let's check this. I got FE is 55.8. S is 32. 16 is 32. 32 is 64. I bet you if I made a mistake, it's right there. 55.8 plus 32. Or if you see it, tell me. If you see it, some place I go 151.8, I got that. 7 times 18, maybe it's that one. 18 times 7, 126. 126 plus, oh, here it is. 126 plus 151.8. Right there, I missed the 1.18. So actually my numbers are a little bit off. So it's 151.8 plus 126 equals, this bottom number is not 287. It is, and this is where I goofed. Okay, and so this number is actually 277.8. So that'll change that. And let me recalculate it for us. 126 divided by 277.8 is equal to, that's the answer, 45. And like I was telling you, it's not 44 like what I got. It's 0.4534. So move that over to, and then our answer is 45.4%. So sorry, I didn't see that right there. I wrote 151.8 here, and when I brought it down, I saw it as 158. Or what probably happens, like what usually happens when I'm trying to talk and write at the same time. That's why people goof up when they go to the whiteboard, because they're thinking this fast and then they can only write this fast. And so you got to disconnect there. All right, so that's number 14. 14, that's the answer. Now it's corrected. Yay. and that matches with the answer key in the back. Remember the answer keys, they never tell us how to do anything. They just tell us what the final answer is. Okay, number 15. So that we can finish this up and then go look for that, some of those chemicals. Number 15, it says compare. Is the percent by mass of copper in copper, what is that? Copper sulfate, 5, penta, copper sulfate pentahydrate, okay? Is the percent by mass the same there as it is in copper sulfate? And the answer, you don't even have to do it, because here, I'll just write it. Copper sulfate pentahydrate, and you're trying to compare that to just copper sulfate. Now, from what we just did, you would calculate the water, it's 18 times 5, okay? And there would be 18 times 5, which is what? You can do that fast. 18 times 5 is 20, that's 90, is it? Yeah, it's 90. All right, so you have 90 grams divided by the total. You would have to figure that out, and then you get some total. But my bad. It's a percent by mass of copper. So this amount of copper looks the same, doesn't it? I mean, it's the same amount, but when you calculate it, the fraction at the bottom is going to be different because now you got 90 grams more at the bottom. So they are going to be different. So number 15, they're different because the molar masses of these two compounds. This is just as one compound. I mean, it's got these water molecules attached to it, but they are loosely attached to it, but they're attached to it. So you have to count them as part of the compound. So if you're trying to find out the percentage of everything, then what you're going to do is your mass of copper is not going to change. Okay. Shoot, maybe we could just do it. All right, I'm going to do it real quick. All right, so copper, let's go. Because if you don't understand what I just said, then I can say it over again and it still won't make sense. So let's just calculate it. I don't know copper by heart, so I'm going to go and take a look. The copper is 63.5. All right, so I got copper is 63.5. Sulfur was 32, wasn't it? Sulfur is 32.0. And then I wrote 63.55, is that right? For copper, 63.546. So yeah, 0.55, but I really don't need this 5. So I'm just gonna lose that. And 32 is for sulfur. And then I've got the oxygens, I got 4 of those. So 4 times 16, 32, 64. So when I add all that up, I'm gonna get 0.5 there. I got 5 plus 4 is 9, and then I have 12 plus 3 is 15. So I got 159.5 grams for this guy. Okay. And then if I were to add the 90 grams, I'm going to have something different. Well, I'm going to put a line down the middle there. Okay. But in order to calculate the percent by mass of copper, that would be copper is 63.5. So it's going to be 63.5 grams in this copper sulfate pentahydrate. So in the whole thing, and the whole thing is going to be 159 plus 90, which is 259, 249. Divide by 249.5 grams, and then I'm going to get a percentage. Okay, over here though, in order to get the percent mass of copper in just this, it'd be 63.5 for just the copper, and then the whole thing, as we saw, is 159.5. So the question is, are these two equal? Is this equal to that? And the answer is no. Because if you look at the bottom, that's going to give you a different answer. Okay. So you can reason that. You didn't have to actually do the problem, but I did the problem for us so that we could more easily see what the answer is, and that's how you do that. All right. Number 16 is a lot of big words. Let's go to 16. 16 says compare and contrast, distinguish between efflorescent and hygroscopic. Woo! Efflorescent and hygroscopic. Well, if it's efflorescent, as you saw from the reading, what that means is that for compounds that are hydrates, they lose their water just sitting there, and so the water evaporates into the air. So that's what I mean by the first one, efflorescent. Okay. Sometimes in a chem lab, what I'll do is inside my fume hood, I have a glass bell jar, and in that bell jar, I have these chemicals in them that are known desiccants. You probably are familiar with silica gel. Like when you buy a new pair of shoes from Zappos, and it comes to your house in a box, it's got that little bitty white envelope this big that's filled with those little gel packets, those little gel chemicals, and it says silica gel, do not eat. You ever seen those? Well, that's the desiccant, and it's sucking up the water out of the air because some chemicals are going to release that water. Some chemicals are, use the word, efflorescent. Ooh. But then other chemicals are how do we say that? Hygroscopic. And so chemicals that are hygroscopic are not going to lose the water to the air, but they're actually going to suck up water from the air. And when they do that, some of these chemicals are chemicals that will form hydrates. So that's how we get the dot 5H2O, things like that. So if you have a chemical that absorbs water straight from the air, then that is a chemical that is hygroscopic. So let me write that. If it's efflorescent, what it does, efflorescent chemical loses water to the air, whereas a hygroscopic chemical is one that it kind of sucks up the water from the air. How should we say that? Suck up. I don't want to say suck up. It removes water from the air, and sometimes it might form a hydrate. Okay. Yay. Are we done? No, we have one more. And this question, just looking at it, it looks hard. But just looking at it, they don't want us to solve anything. Let me read it, because I'm kind of talking and trying to read it at the same time. But if I read it to you, I'll be reading it to me. Number 17 says, which of the following substances dissolve to an extent, to a significant extent in water? Say, which of these following substances dissolve in water? Oh, you don't have to calculate anything? That's good. It says, explain your answer in terms of the interaction between solvent and solute. Explain your answer in terms of the interaction between solvent and solute. Oh, okay. So remember, the solvent's going to be basically water. So they're saying, well, how does this react with water, and why would it dissolve in water? Okay. From the very beginning, remember, if it's water's a polar molecule. So if something is ionic, or it's made out of, if it's a crystal that's made out of ionic bonds, or if it's a polar covalent compound and it has a slight positive and negative charge, then it's going to react with water, and it's going to dissolve in water. So for those two types of chemicals, let me write those down. Ionic and polar covalent are going to react with the water. So if they're ionic or they're polar covalent, then they're going to dissolve in water to some extent. Is that what they wanted? Yeah. Which of the following substances dissolve to a significant extent in water? So if they have these types of bonds, then they will dissolve. So let's look at them one by one and see if they have, see what kind of bonding it is. All right, first one is CH4. CH4 is covalent, but it's nonpolar, so it's not going to dissolve. So if I were to draw at CH4, it would be like this, like central carbon, and then the simple way to draw it is like this, with the carbon and the 4 hydrogens around it. Okay, so there's no pole. There's no part where an electron would be going across these bridges and say, hey, you want to go hang out over there? Because that H has more fill in the blanks than the other H. No, all these H's are the same. So if you're an electron whizzing around, you go over here, it's the same as going over here, which is the same as going over here, which is exactly the same as going. So there's going to be an equal distribution of electrons around this carbon at the different hydrogens. So there's no pole. So this is going to be insoluble. It's not going to dissolve. It is not going to dissolve because it has a non-polar covalent bond. Remember, if it's a line like this, this represents a covalent bond. And so these are non-covalent bonds. So that's 17A. 17B is an ion. 17B is KCl. And KCl is going to dissolve because this is a K plus and this is Cl minus. You remember doing that from way back in the day. That's chapter, I don't know, 7 or 8 or something. Whew. So this one is soluble. Why? Because it's an ion. It's soluble. What do they want us to say? It's all soluble. This is insoluble because it's nonpolar. This is soluble because I just put a comma, I guess. This is soluble because it's an ion, or has ionic bonds, I guess. All right, let's go to C. What is C? C is I2. That's iodine. Iodine, remember, is one of those diatomic molecules. There are 6 that make 7. What does that mean? It means there's 6 molecules, or 6, not molecules, there's 6 elements that form a 7. And so those are the diatomic molecules that go into the periodic table. These guys right here, 1, 2, 3, 4, 5, 6. Those 6, can you see the number 7 in there? That's the number 7. There's 6, and they make the number 7. So all these in nature are diatomic, which means that their most stable form in the air is with 2 atoms that are connected, like O2, like N2. This is 78% of the atmosphere. This is 21% of the atmosphere. But these other guys, these halogens, they exist also as a diatomic. So F2, Cl2, Br2, I2. So those are all diatomic molecules. Those are your 6 that make a 7 in the periodic table. All right, so if we look at it, I2, if I were to diagram it out like I did here, it's I and I. And this is your covalent bond. And again, if we follow the path of an electron, there's no reason to go to the left over than to the right. So So this is also then going to be insoluble because it is also nonpolar. So insoluble nonpolar. So that's letter C. Cool. Letter D, MgSO4, magnesium sulfate. I hope you recognize this as a polyatomic ion, right? Because this thing right there, SO4 is a 2 minus, but magnesium is 2 plus. So that whole thing is balanced, but this is an ion. This is an ionic compound, which forms a crystal. And remember, if you take a look at the periodic table of elements, then you're going to see that this magnesium is in the second family, 2A. So because it's in the second family, the first family has a plus, and the second one that they ionize has a 2 plus. Those are the alkali earth. And then here, this is one of the polyatomic molecules that's the polyatomic ions that's in your polyatomic ion list. I don't know if you remember, but this is way back in it from when I said, well, we use this table so often that some books put it right next to the periodic table. Your book doesn't, but I have a post-it on mine in my book on page 268. And if I look for SO4, SO4 is 2 minus. So you got 2 plus and 2 minus. These are ions. So because they're ions, what I write for ions, soluble, they will dissolve in water because this is ionic. So that's letter D. Okay. All right, let's go to 2 more. Got E and F. E and F, sucrose. Sucrose is table sugar. Someone at my house, my 20-year-old and his girlfriend, they made chocolate chip cookies yesterday. Whoa, good stuff. In fact, next break, I'm gonna go get one. It was like they used a recipe, but it was tasted like a Toll House cookie, which are the best, right? When you bake chocolate chip cookies, but the tasted like a Toll House cookie that they added like a little bit of cocoa powder to it. Ooh, that was good. I'm gonna have another one. So anyway, sucrose. Sucrose is sugar. You don't remember from your organic molecule chapter, this is a disaccharide, a double sugar. So remember the monosaccharide glucose is C6H12O6, and with sucrose, it's C12 because it's a double sugar. So the first sugar is C6. Well, this is C12. So this is a double sugar, C12, H22O11. The number of hydrogens is going to be double the number of carbons, basically. But remember, in order to bond these things together, you have to take out a water molecule. If you remember, this is called dehydration synthesis. This is from first semester, right? And so every time you join those parts, you take out a water molecule. And if you were to take out the water molecule from, here, I'll just do it real quick. This is an aside, but C12, it'd be, if the number of H's is double to the carbons, it'd be 12 and 24. And this would also be 12. Okay. But in order to get those two parts together, you got to take out a water molecule, and the water molecule is H2O. So if I were to subtract that out, then that's going to be C12, H24 minus 2 is 22. 12 minus 1 is 11. And so ta-da, that's how we get the formula right there. But that wasn't even the question. The question for this is sucrose. Well, sucrose, as you know from your experience with coffee, is going to dissolve, right? So it is soluble but it's soluble for a different reason from these guys. It's going to be soluble because it is a polar covalent. It has polar covalent. It has covalent bonds, but it has a charge closer to one side. So it's a polar covalent molecule. And then the last one, NaHCO3 is F, NaHCO3. Do, 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 do. And that is going to be, gosh, what do we call this? When we have baking soda, it's called hydrogen carbonate. So that's this right here is, where's my pen? This is a plus, and then this right here, the hydrogen carbonate is going to be a minus. So this is an ion. So this is going to be soluble also, because that, like I said at the very beginning, if it's ionic, it's going to be soluble. And so this is an ion. And so for our last one, this is soluble, soluble. I forgot the L, soluble. And it's because it also is ionic. Wow, how many pages was that? Well, it's because I have to write bigger than you do, but 4 pages for that one.